Hello, today we're going to talk about multi-physics electric motor design and simulation using the Motor-CAD software tool. We're going to start with a brief introduction to the Motor-CAD software and the different modules, how they work and what they do. We'll then go into the software and do a live demonstration of the features within the software. So, Motor-CAD software is a tool for the design of electric motors. It has three modules, an electromagnetic model, which is a combined finite element and analytical based method for calculating electromagnetic and electrical performance of rotating electric machines. The thermal model is mostly based on a lump parameter thermal network approach, which is automatically set up based on the geometry input by the user. The lab module is used to calculate the performance of electric machines over their full operating range. This allows you to do things like efficiency maps, torque speed curves, continuous thermal envelopes, and duty cycles. The Motor-CAD software is designed and developed by a team of electric machine experts, and the tool is very well suited to the needs and requirements of electric motor designers in industry. So I'll start with the Motor-CAD EMag module. It's mostly based on a 2D transient finite element based approach with some analytical methods as well for different machine types. We use the electromagnetic module to calculate things like torque, power, efficiency, torque ripple, etc. It can also be used to do things like calculate losses, so the copper loss, the iron losses, the frequency related losses in the winding, and eddy currents in solid components such as the magnet or the shaft. The idea with Motor-CAD is it's very easy using its template-based editor to set up geometries and do advanced calculations quickly and easily. However, it is also flexible enough for you to experiment with many different options, such as the winding or by importing your own geometry from a DXF. The Motor-CAD EMag module covers a number of different motor types, brushless permanent magnet, both inner and outer rotor, induction machines, synchronous reluctance machines, switch reluctance machines, and synchronous wound field machines. You can see on the screen a number of different plots that can be generated by the software, and you can see in the bottom left-hand corner some plots from calculating the eddy currents in a bar type or hairpin winding. The software has been comprehensively validated across many different types of motors with lots of different calculation methods using experimental data. The thermal module, or Motor-CAD Therm, is probably what the Motor-CAD software is best known for, and it is the standard tool in industry and academia for calculating the thermal performance of electric machines. It works using a lump parameter thermal modeling technique, which is automatically set up based on the inputs of the user, such as the geometry, the materials, and the cooling type. Behind the software, there is a set of correlations and practical experience that allows the lump parameter to be set up automatically, and it can give very accurate results. It also provides very good understanding of the main heat transfer paths and allows engineers to optimize the cooling behavior of the machine. The thermal resistance network that's automatically set up is a three-dimensional network. So it's a three-dimensional analysis that includes things like cooling in the end space, cooling off the end windings, the effect of the rotation on the airflow, and the heat transfer in the axial directions of the machine. Using Motor-CAD, you can do both steady state analysis or continuous performance analysis, or transient as well, using either simple duty cycles or more complex duty cycles, and we'll demonstrate some of these later on. Motor-CAD covers a number of different cooling types, everything from totally enclosed non-ventilated to fan-cooled, air-cooled, water jacket-cooled and oil-cooled machines. One of the big challenges in the field of thermal analysis of electric machines are that there's a number of manufacturing effects which have often significant influence on the performance of the machine. Some examples of these would be the quality of the impregnation in the winding, or the interface gap between the stator lamination and housing. Motor-CAD has some built-in experience to guide users and engineers to input reasonable numbers here that give a good correlation with the majority of machines that we've seen tested in labs. So the final module we'll talk about is Motor-CAD Lab. It's a module which allows you to analyze the machine performance over the full operating range of the machine. It applies a control strategy so that things like the optimal phase advance angle is automatically calculated, and field weakening behavior is automatically calculated by the software. You can do things in lab, things like efficiency maps and duty cycles. It works by initially building a model based on the finite element. So it sweeps the performance of the machine through a range of different current magnitudes, phase advance angles and frequencies, and builds an equivalent model of the machine based on the finite element. That equivalent model is then used with a control strategy to calculate performance across the full operating range. This is an example of how we could take a vehicle speed profile for example, for an electric vehicle. You use that with a vehicle model to calculate a time, torque and speed requirement. Using Lab, we can then calculate the performance of the motor that's required to produce this time, torque, speed behavior, and it will output a loss versus time value. We can then solve this with a thermal model to give us a temperature rise over that duty cycle. This allows us to size the machines and optimize the machines to achieve a particular performance over a worst case duty cycle. Another type of calculation that you can do in Lab is the thermal envelope, or thermally continuously limited envelope. This allows you to input, say, a maximum winding temperature and a maximum magnet temperature and solve the torque speed curve of the machine across the speed range to understand what the continuous operating limit of your machine is. So we're now going to open the software and show how Motor-CAD can be used for the design and simulation of electric machines. When you first open the software, you're presented with the radial cross-section of the machine. What you're looking at the moment is a 48 slot, 8-pole interior permanent magnet machine. It's a typical machine used for electric vehicle traction. There are 3 modules within the software: the electromagnetic, the thermal, and the lab. We're going to start with the electromagnetic, move on to the thermal, and finish with the lab. To start in Motor-CAD, you have to input the geometry of your machine, and you do that using this template editor, the parameterized template editor. We input the number of slots, the number of poles, and some geometric parameters such as the tooth width and the slot depth. If I update these parameters such as the tooth width, you can see that the machine design is redrawn here in the image. There's lots of different templates available in Motor-CAD for lots of different machine types and rotor types, and you can see here, for example, all of the different rotor templates that are available for lots of different permanent magnet machine rotors. Once we've defined the radial cross-section, we then look at the axial cross-section of the machine, and we can define things like the length and the magnet segmentation and the end winding dimensions. And then the geometry can be shown or visualized in this 3D viewer, and this 3D geometry can also be exported to various different CAD packages. After we define our geometry, the next stage is to look at our winding definition. The first step is to lay out the coils in the winding using the pattern editor. We have to specify the number of phases, the number of turns, the throw of the coil or the coil pitch, and the number of parallel paths. We can then see each phase of the winding plotted onto the machine geometry. Motor-CAD offers an automatic winding editor which gives you an optimum winding layout, but you can also override this with a custom winding layout and input your own coils individually. Once you've input the winding, you can then see some information about it. We plot the winding phasor diagram. We show the MMF harmonics, and this gives you an indication of things like the leakage inductance and the how high the rotor losses will be with this particular winding. And we can also see the winding factors and see how the air gap field is filtered by the winding and how well utilized the fundamental torque producing component of the air gap field is. After we've defined the geometry and the winding, we then move into the input data where we specify the materials of the machine. Motor-CAD's got an inbuilt database with lots of typical materials used in electric machines. You can see here all the different materials in the stator lamination database and also the magnets here. In this design we used N250 35A steel and N30 and magnet, which is a neodymium ion boron magnet. If we wish to add our own material which is not already in the database, we can do this here. For example, for your electric steel lamination, you can specify a BH curve, and you can also populate a set of losses at different flux densities and frequencies. Motor-CAD then takes this loss data and generates some Bertotti or Steinmetz loss coefficients, which are used in the calculation of iron losses. As well as electric steels, we can obviously add our own magnets as well, or conductive materials. So once we've defined the geometry, the winding layout, and the materials, we then move on to the calculation page where we specify the operating point and set up the calculation. So here I've specified a shaft speed of 4,000 RPM and a peak current of 324 amps. We could also specify current as an RMS quantity, or we could specify it as a current density, which is quite useful when you're doing machine design. We also specify the phase advance, and there's various different options for coupling between the EMagnetic module and the thermal module. At this point, because we haven't introduced the thermal module yet, I'll put no coupling on, and I'll just specify the temperature at which we want to do the calculation. So I've specified the temperatures, and then all I have to do now is check the various different calculations that I want to do. There's various different calculations available: cogging torque, demagnetization, and on-load torque. In this example, I've just checked back EMF, which is an open circuit calculation, and on-load torque. Once I've checked those, then I just click solve, and what happens here is the calculation set up and the finite element solver starts to calculate performance. While it's solving, I can go to the eMagnetics tab and I can see the finite element being solved. The solver in Motor-CAD doesn't require the user to input things like meshes, boundary conditions, or symmetry. It's all automatically set up. We can also see while it's solving the graph information being input here. And this is the sort of data that's been extracted from the finite element calculations. So I can see things like back EMF, on-load voltage waveforms, torque waveforms, and flux linkage waveforms. The solver's designed to be very fast, and within about 40 seconds there we did 2 transient finite element simulations across a full electrical cycle. As well as this numerical graph data, we can also go to our output data tab here, and we can look at a number of parameters that have been calculated based on our calculations. So these are things like the voltages, the inductances, short circuit currents, torque, flux linkages, power factors, power, flux densities, and torque ripple. We can also plot the phasor diagram of the machine, and we have also calculated a number of losses for the machine. We did 2 different calculations there. One was an open circuit calculation, and you can see the losses for those on the right hand side, and the other was an on-load calculation, and you can see the losses there on the left hand side. One thing that Motor-CAD does, which is very useful, is splits the losses between different parts or components in the machine, and this is very important when it comes to thermal analysis, to make sure that the losses are injected in the correct node of the thermal network. We can also investigate the finite element plot here. If I hover over this, I can see the flux densities at any point on the geometry and at any sort of rotor position. I can also view the losses, and here I can look at my hysteresis losses, both major and minor loop hysteresis losses in my electric steel laminations. I can look at my eddy current component loss, and I can also look at the losses in the magnets. The eddy current losses in the magnets have been calculated using this 2D finite element solver, but we correct using an analytical equation for the axial cross section so that the eddy currents are calculated correctly. One other thing that you can do in Motor-CAD is, if you want to have more definition around your geometry that is not described exactly by the parameterized editor, you can actually bring in a DXF or do some scripting of the geometry. I can demonstrate this here using this FEA editor, and what I'll do is I'm going to import a DXF and click this Use DXF EMagnetic button. I can then move some regions around to tell the software where my flux guide regions are, and then I can just simply resolve the finite elements. If I go back into my finite element plot now and show the flux density, you can see that the geometry now being solved is not the parameterized template editor, but the DXF geometry that we brought in. So that's a brief overview of the EMag module. There's lots of functionality that we didn't go into very much detail here. We didn't look at, for example, how you can do custom current waveforms, how we can do multiple skew slices, but it's just a simple introduction to give people a feel for what the capabilities of the software are. We're then going to move into the thermal module, but to do this, I'm going to start by generating some losses using the EMagnetic to thermal coupling option to calculate losses in the electromagnetic. and pass them into the thermal module. To do that, I simply click on this E-magnetic losses to thermal option and check the calculation that I want to do. I'm going to continue with this 4000 RPM, 200 Newton meter operating point to see what kind of temperature my machine gets to when it's operating at that condition. Other coupling options also include an iterative procedure where we can pass losses to the thermal, calculate temperatures, bring temperatures back into the electromagnetics and recalculate, and you can converge these models together as well. For this example, we're just going to do a simple passing the losses across. To switch into the thermal mode, I simply go into the Model tab here and I move from E-magnetic to thermal. You can see in the thermal module that there is some extra geometry parameters here. This is because the housing in the thermal model obviously has an impact on the performance, and in this case we've got a water jacket cooled machine, so we have to define the dimensions of the housing, we have to define the dimensions of the water jacket. You can see here in the axial cross section, for example, that you've got the water jacket dimensions and the housing that has to be specified and set up. As well as the extra geometry inputs, there are a few other things that we have to define in the thermal module. For example, we have to specify our cooling type. In this case, we've got a water jacket, so I've got the housing water jacket cooling option checked here, but you could have other options such as through ventilated or self-ventilated or spray cooling. When you select a particular cooling type, a tab will appear which allows users to set up that particular cooling type. So here with my with my water jacket, I need to specify things like the fluid flow rate, the inlet temperature, and the fluid properties. I've also got some extra materials to define in my thermal module, things like the wire insulation, the impregnation, and the slot liner. And the important aspects of those are things like the thermal conductivity, specific heat capacity, and density. There's some pre-populated values in Motor-CAD which are typical values for materials used in electric machines in case this information isn't available to the engineer when they wanted to do calculations. We can move to the losses tab, and you can see here that the losses have been calculated from the electromagnetics and passed into the thermal module. So we don't need to change these losses here. And once we've set up our extra materials, geometry, and cooling type, we can then start to do some calculations in the thermal module. To do that, I move into my calculation tab, and you can see I've got some different options here: steady state or transient. We're going to start with a steady state temperature calculation. So we want to know what temperature the machine is going to get to if it runs continuously at this 4000 RPM, 200 Newton meter operating points. So I press solve, and I can see that the thermal module has solved the performance almost instantaneously, and I'm presented with this representation of the lump parameter thermal network. Throughout Motor-CAD, the colours are always consistent, and they always refer to particular components in the machine. So the yellow is the winding, the red is the stator, and the blue is the housing. And I can see here, for example, that my winding gets to a peak temperature of 170 degrees at this operating point. I can also plot the temperatures onto the geometry. So I can see, for example, I can look into my radial cross-section and see what the temperatures look like on here, or plot it onto the axial section as well. As well as doing steady state analysis, we can also do transient temperature calculations. To do this, I first need to set up what kind of transient calculation I want to do, and I can do this in the duty cycle data here. So I've set, in this case, a simple transient, and I specified 600 seconds. So what I'm asking here is what kind of temperature the machine is going to get to after this 10-minute period. So I select transient here, and I click solve. You can see that very quickly the thermal transient behavior of the machine is calculated. Again, the colors are corresponding to the different components of the machine. So the yellow is the winding and the red is the stator. And I can see here after 10 minutes that my winding reaches a hotspot temperature of 156 degrees. We can also do much more complicated transients in the thermal module, and we will demonstrate that, but we're going to use the lab module to generate the data, the input data that's needed to do this more complex duty cycles. So I'm going to move on to the lab module, which is the final module that we are going to demonstrate today. And I'm going to click here on the model drop-down and select lab. As we described in the sort of initial introductory presentation, the lab module works by initially sort of building a model of the machine based on the finite elements. And that's done using this model build tab here, where we specify something like the maximum speed, the maximum current, and then we click the build model button. I'm not going to demonstrate it right now because it will take a few minutes to calculate. So this is something that we've pre-calculated for this demonstration. But the calculation is very quick. So the idea behind the software is that everything can be done iteratively, and we want to be able to do all these calculations within minutes. So we build the model, which will take maybe 10 minutes, 5 or 10 minutes to do, and then once we've done that, we can move on to our electromagnetic tab. So the first thing that we do in the electromagnetic tab is we might want to calculate the torque speed curve of the machine, or the peak performance curve of the machine. So I select maximum torque speed curve, and I click calculate electromagnetic performance. And you can see a window appears with the torque speed curve. So it calculates very, very quickly. You can see here that it's showing that with this 480 amp peak maximum currents, I can get about 287 Newton meters. At a certain point, I run out of voltage and then I go into a field weakening mode. And you can see how the torque falls as we have to advance the current angle to stay within the voltage limits. If I select the phase advance value here in the drop-down, I can see that the software has chosen the maximum torque per amp current angle at lower speed. Again, then once we hit the base speed and we run out of voltage, the phase advance is increased to stay within the voltage limit. There's lots of other parameters available to plot. For example, we could look at our line voltage, or we could look at our power. We can see that the machine in this situation is capable of a peak power of about 130 kilowatts. As well as torque speed curves, we can calculate an efficiency map. Again, this can be done very quickly once we have the pre-built model. And you can see that we've calculated now the efficiency map in both the motoring and generating mode, and we can see a peak efficiency region of this machine at about 97%. We can view other parameters as well. If we want to, we can plot things like flux linkages, phase advance, or loss maps, and we can click anywhere on the plot to see the value. All the data is also available in a tabular format, and this can also be exported to things like Excel and MATLAB. One of the other things that we can do in lab that it's very useful for is calculating duty cycles and drive cycles. So you've got two options. You can either use the built-in vehicle model and input things like the mass, the frontal area, and the drag coefficient, and use a particular time, speed, drive cycle, or we could import our own time, torque, speed cycle. If, for example, you have your own calculation of drive cycle, or the application isn't a vehicle application. Once we've got a drive cycle, we can actually plot that onto the efficiency map, and you can see each one of these points that I've plotted onto the efficiency map represents 1 second on this drive cycle that I've specified. You can see that the performance is clustering around medium to high speed and at lower torque. And we can maybe use this to try to optimize the efficiency of our machine to work at the most common points on our standard drive cycle. We can also calculate performance across that duty cycle. So we can take each one of those points and solve the performance of the machine, the required current, phase advance, and corresponding losses for each one of those time, torque, speed points. So here I'm showing the drive cycle that we specified. This is the speed profile over time. This is the torque profile over time. And you can also see things like efficiency and power and current and voltage. But most importantly, we've got the losses. So we've got all the different loss components and how they're varying over the drive cycle. So far with lab, we've only really coupled the lab module with the EMagnetic solver to calculate electromagnetic performance, but we can also couple it with a thermal model to get thermal performance. So, for example, we could take this loss over time with a duty cycle and export these to my thermal model to convert this loss over time into a temperature rise over time. So I go back to my thermal module here, and I go to my duty cycle definition, and you can see that that loss data has now been brought in. And if I click on this transient solve button now, it's going to calculate the temperature rise of the machine over this duty cycle. While it's solving, I can click the show updated results to see how the temperature of the machine changes over time. If I now return to the lab module, one other thing that I can do, which is a very nice feature and we use quite a lot in our design and analysis work, is to calculate the continuous performance envelope. So we take the machine model and we specify a minimum speed and a maximum speed, or a speed range that we want to calculate over. And we also specify, say, a particular temperature limit for both our winding and our magnet. In this case, I've specified a maximum average winding temperature of 160 degrees and a maximum magnet temperature of 140 degrees. We can then calculate performance over that torque speed curve, and we get a resulting continuous torque speed curve continuous limits. So this shows that we can do approximately 200 Newton meters at low speed, and if I look at the power, I can see I get maybe 80 kilowatts before performance starts to fall off at high speed. If I want to investigate where the limits are, I can choose the temperature here, so I can see what my average winding temperature is, and I can see what my magnet temperature is for all of these points. And what I'm showing here is that up to about 3000 RPM, the machine is temperature limited based on the winding temperature, and from about 3000 to 10,000 RPM, the machine becomes limited on the magnet temperature. So if I wanted to optimize the performance of the machine, I might focus on trying to control the temperature of the rotor in this example. So that was a very brief introduction to Motor-CAD and some of the main features. There's lots of different functionality that we didn't describe today. But if you would like more information about Motor-CAD or would like to arrange a trial license, please contact us on the website and we'd be very happy to talk to you.